Hello everyone and welcome to this next lecture on Python Power Electronics, and this will be the concluding lecture on the series of operation control of an uninterruptible power supply. So up till now, to begin with, let's go over to the project folder, that is single UPS simulation. And up till now I covered almost all of these. The last was this closed loop current control. Let's go over and see what happened. So in closed loop control, I was talking about how we are transforming the three-phase AC currents into a synchronously rotating DQ reference frame, and by doing so we are converting the currents to a DC value. And because the current and the references are DC values, you can use a PI controller to track it with zero steady state error, as in this case. Right? The switching is inevitable because you have a switching, it's a switching converter, but otherwise if you see, there is no DC offset, there is no error, steady state error. So now the question is, this resulted in an output voltage of this nature, and I already said that this output voltage is not a regulated voltage. For example, if I were to consider a 208 volt 60 hertz typical voltage, alright, this 208 volts is a three-phase RMS voltage, and that means it is 120 volts single phase RMS. And that 120 volts again translates to 170 volts peak. So if you see here, I'm not even close to 150. And what this means is that my voltage is not regulated. I have balanced sinusoids. I have a three-phase balanced sinusoidal output voltage. So that's good. But it's not regulated to a magnitude yet. So this is still not good enough to apply to any particular load, particularly a load that's sensitive. So for that, what we have to do is we now go to the next stage, and that is we go over to closed loop control. So in closed loop control, since rather than me talking, first I'm going to just launch the circuit simulator, and as usual go into the virtual environment. As always, first thing you must do, always activate your test environment. So you see Python test, and the version is 3.5.3. So now that we are here, let's go into the project simulator folder, and I will say Python -5. That's all. So I just have to launch the circuit simulator, because instead of actually going through the circuits, what I'm going to do is I'm going to run this simulation, and then I'm going to talk about the circuits later, because the simulation takes some time to run. So instead I will use this time to talk about the simulator. That will save some time. So as always, paste that file, the URL, and I'm there. So let's go over to the simulation library, and you see the last simulation is single UPS inverter output current control. Alright, so we have to start the next one. So let me call this single UPS output voltage. Let's call this closed loop control, just to be absolutely unambiguous. And let me paste this here. The rest of them can stay as it is. Let me go over and get the directory. Now, just to remind you, this circuit is exactly identical to the circuit before. Exactly identical. And we will see this afterwards. I want to just get this circuit simulator up and going. Save simulation parameters, everything is okay. So we go to the next page and we add the circuit simulator. So as I said before, just to tell you, there are several files. So first and foremost, the most important is inverter bridge, because this is the DC to AC converter, three-phase DC to AC converter. After that comes inverter filter, which is the LC filter. After the LC filter comes bus connect, which is the feeder at the output of the inverter, and the last is the three-phase load, okay, which is simple RL load. So let's just add these circuits first. So as always, go to that directory, inverter bridge, and let's call this inverter bridge, right? choose file. The next one is inverter filter. Let's call this filter. And after that comes bus connect. Actually, this name is not really nice. If you want, you can change it to something like 3-phase feeder or something like that. So I just call it feeder. And then last is 3-phase load. So 3-phase. We'll just call it load. And it's all done. As always, whenever you make a change or when you first add the circuits, always click process circuit schematic. Okay, as always, go down and check the circuits do not have any detectable errors. So we are ready to go. So now we add the circuit parameters. So first is bus connect. So I'm going to just speed this up by uploading this file. Bus connect parameters. Upload it. Inverter bridge. And I shall upload the file inverter bridge params. So basically any file underscore params.csv is the parameter file for that particular file. That's all. And you see it has uploaded. Back to circuit list, inverter filter, choose this file, choose inverter filter params.csv, upload the file. And these are all done. Yeah, the parameters are updated. Go to the circuit list. Then the last is 3-phase load. Click on 3-phase load.params. Already selected. File. And this is also done. So it's just an RL load. So now that this is done, we go back to the edit control. Now in edit control is going to be a little different. We will have, as usual, like in the previous case, we have the inverter current control.py. We will have the inverter modulator.py, which is the pulse width modulation. This is the current controller. This is the pulse width modulation. And the last we have the PLL. PLL is just to check if the frequency is okay. I'm not even going to look at that. You're welcome to add those files. Now, in this case, we have one additional control file. And that control file is inverter1 voltcon.py. As you can think, this file, this control file, is the voltage controller. Alright. So I'm going to add 4 files in this case, not 3. The previous case was 3. Now it's going to be 4. So let's go from inside out. Right? I mean, you can do either way. Inverter modulator. Let's call this pulse width modulator. And there's a reason. I mean, it's called inverter. And we'll call this PLL.py. As your simulations become bigger, it's better to write more and more descriptions. That's easier for you to figure out what you're doing. Inverter current control.py. And the last is the inverter voltage control.py, voltcon.py. Alright, so this is it. Now let's go configure them. So the first one is inverter current control, current con.py. So as always, there is a file _desk, which is a descriptive file. You just have to add it, upload it. And you see the variables have been added to the database. Go back to the control page. Next one, inverter modulator, and inverter modulator _desk.csv, the descriptive file. Let's upload this file. And it is done. So let's come down. You see it has uploaded all the variables into the database. The next one is inverter voltcon.py. Next was voltage controller. Upload this file. And you see all the variables are entered. And then there's one last one, PLL. Let's call this PLL.py and upload it. Oh my god. Okay, I made a bad mistake. You see what happened? I actually should have uploaded PLLdesk.py CSV, alright? And instead of doing this, I actually uploaded PLL.py, alright? Now the problem with doing this is I have not yet included the error checking to make sure that this is a descriptive file. So if you upload this file and it's the wrong file, if you upload this file, it doesn't know, it cannot read this file. And because it cannot read this file, it still tries to read it, you get that error. So do not upload any other random file. For example, don't add this text file or something, you'll get that error. Alright, so anyway, that's interesting. It's a good thing that I made this error so that you can actually have a look at it. So now it should work. This is a descriptor file, PLL_desk.csv, and you see now the variables have been added. So we are done here, and we can go to the last one, that is V output. As always, let's run this. It says running, but as I said, always go to the main page. Now these errors are from that PLL.py file. Okay, that was a mistake. This is different. Always look for the last one. If there's an error here with respect to the last request, it means there is really an error in the simulation. This is working, no problem. So now this is working, as always, let's add something because you want to see what it's doing. So let's look at the output currents. Output currents are, or let's call this output voltages. Let's add the output voltages. And as before, let's plot the filter outputs. Voltmeter filter A, we call this VA, save this waveform. Voltmeter filter B, VB. Voltmeter filter C, VC. Let's click on done. We now have the first plot. So let's plot this. And let's go to the folder. There should be a plot, and there it is. So as I said before, initially almost every power electronic circuit will take some time to stabilize, so this doesn't look like much. Alright, we wanted to see output voltages, and I don't know what this is, but the simulation is running. It will take some time to run. What's important, as always, is it's not all 0, and it's not something like 10 raised to 37. If it's 0, then you have a problem because something's not connected. Alright, you have a connectivity problem. If it's 10 raised to 37, it's a problem because you have instability. This means it's working. So now that it's working, let it run for a while, and in the meantime I'm going to tell you a little about, let's go look at the control files, and let's look at this. Let's first look at the circuit. The circuit as before in the previous case is exactly the same, but I'll just go have a look anyway. So this is it. So you see here it's the same as before. It's a 3-phase DC to AC converter. What this means is there are 3 legs. Each leg has an upper switch and a lower switch, and each switch has its anti-parallel diode, and we are taking the midpoint out to form that particular phase of the inverter as that phase of the inverter. So these 3 phase outputs go to the next file, that is inverter filter. To know how these are connected, simply follow the jump labels. For example, in this case you see the there's a jump label is jump inverter 1 phase A, and if you come here, and of course the remaining are jump inverter 1 phase B and phase C, and if you were to come to the next file, you will see these jump inverter labels are there, and when you see this two corresponding jump labels, it automatically it means these two are connected. Alright, so as before, you have a resistor and inductor. Basically it's an inductor with its parasitic resistor, and you're measuring the current through it, and of course there are these 3 jump labels, and there is a 3-phase capacitor bank which is basically star connected with an isolated neutral. So it's an LC filter, and at the output of this inductor, of this LC filter, there is again an inductor with its parasitic resistance, and we are measuring the output. So now this inductor is actually not necessary in this case. It will be necessary in the next case when we talk about two UPSs, but now not really, but still I have left it just in case. As before, these are the jump labels. So let's look at the next file, and the next file should be bus connect. So this bus connect, again, like it said, it has this jump label, jump inverter 1 out A, and here it is jump inverter 1 out A, so out B, out C. So these two are connected. So this is how it is. At the output I have just a feeder, which is basically a parasitic resistance, and we are measuring the current through it, and we are measuring the voltage across it. The voltmeters are basically 3 voltmeters connected in star with an isolated neutral. You can connect them any way you want. You can even connect them in delta. You're welcome to try that out. And at the output is again a resistance and a parasitic resistance and another ammeter. We are measuring the current. And this one is jump load 1A, load 1B, load 1C. So let's open the last file, that is 3-phase load, and we will see that. And you see these are the same 3 jump labels: jump load 1A, load 1B, load 1C, and connect to that is a resistive inductive load. Alright, this is not a parasitic resistance, this is a load resistance, and this is not a parasitic inductance, this is a load inductance. This is actually a load, and we are measuring the load current. So now that we have shown you this, what exactly are we trying to do? What we are trying to do is we are trying to regulate the voltage across these filter capacitors. If we regulate the voltage across these filter capacitors, we are essentially regulating the output of the UPS, because this is the output. Everything that comes to the right of this bank is the output of the UPS. So if we regulate the voltage across these three nodes, we are regulating the voltage that is fed to any load. Alright, so let's go back and let's look at our control files now. So let's open closed loop voltage, closed loop current. So let's open. Now let's go back and open current control.py. Now if you remember, I'll just zoom in a little because apparently it's too small. Yeah, a little better. Actually maybe a little even better. Yeah, that's better. So now if you see, this is exactly, and if you want to compare, this is exactly the same current controller which was there in the previous case. Alright, and if you don't believe me, let's open that. Alright, you can actually do a scan of this and you'll see it's exactly the same. There's a few differences and I'll tell you what those differences are. In the previous case, we were setting a current reference arbitrarily in the D and Q domain, because like I said, we were doing all our control in the synchronously rotating DQ reference frame. So then we were setting some reference to the D and some reference to the Q. These were just 10 and 10. Now you see they are no longer set to constants. This is some other variable that we are seeing here. Alright, what is this? And if you were to look what is this, you'll feel that, and as I said before, we were initially setting some reference current. We were controlling the output of the inverter to that reference, but the problem is the output voltages were not regulated. So now the question is, how do you regulate the output voltage? And the output voltage is regulated through the controller. This is not the one. Let me close this one. voltcon.py. This is the other controller. So the way it works is, the inverter controller forms the inner controller and the voltage controller forms the outer controller. So what do I mean by outer controller? What does the voltage controller do? The voltage controller does a very similar activity as the previous case. That is, we are again transforming three-phase output voltages to the synchronously rotating DQ reference frame, and that's what this is. Okay, and this time we are setting the reference of the three-phase voltages to be set. So these are the reference. If you see here, I am setting a Vmag ref. Vmag ref means reference magnitude. And what is Vmag ref? You see, it is 208 volts. So I am setting a reference value of the to be 208 volts, the way it would be in, let's say, US. I mean, like right now I'm in Montreal, Canada, but typically this would be anywhere in US, Canada. It would be 208 volts, 60 hertz. All right, that's the residential voltage that we get. So that's what it is, and the frequency is set to 2 pi into 60 hertz. So with respect to this, I am now generating three voltages, Vref A, Vref B, Vref C, which are sinusoids with a magnitude corresponding to that 208. So 208 divided by square root 3 will give you 120, and that multiplied by root 2 will give you 170, which is what is the phase peak voltage of the phase, all right, or the peak value of the phase voltage. And this is given, and we're just multiplying by sinusoid. Okay, and sinusoid, and there's 120 degrees and 240 degrees. So these are three balanced regulated sinusoids. We are now converting these to the synchronously rotating DQ reference frame. Alright, so just read in that PLL paper. I won't talk about it again here. Now once we do this, we are now going to measure the same input voltages. Volt A, volt B, volt C are the measured values of the voltages. Alright, okay, if you want to know this, just go over to the configure control of inverter voltcon.py and you will see what these inputs are. Okay, now after that we are then converting it to the synchronously rotating DQ reference frame. So this is the transformation of the actual measured output voltages to the synchronously rotating DQ reference frame. Now there's something else we do. We are measuring the output currents of the UPS and also applying the synchronously rotating DQ reference frame. Right? Now let's hold your horses. I'll just come to this very soon, why we need to do this. And the last, this is actually not necessary at this stage, but this is just for your own information. We are calculating the active power and the reactive power with respect to the measured voltage and the output current. Okay. Now that this is done, what are we doing? Now comes the control. First things first, we are going to measure the error of the reference voltage from the actual measured voltage, and again this is in the synchronously rotating DQ reference frame. We then integrate it. That's what this is. And after integrating, what are we going to do? Before, when we integrate it, we would apply the PI controller and we would directly set it to the modulation index. Now we can't do that. Why can't we do that? Let's think about it. The problem is, if I look at this, I have an inductor and I have a capacitor. This is a second order filter. The relationship between these capacitor voltages and the inverter voltage is a second order differential equation. When you have a second order differential equation, you have a second order system. And when you have a second order system, if you cannot apply PI control directly to it. Why? Because if you just go back to your regular control theory, if you apply PI controller to a steady DC value, you will get zero steady state error. If you apply PI controller to a linear, let's say a linear signal or anything else, you will get a steady state error. But if you apply a PI controller to a second order system, you will get an increasing error. It will not track at all. And that's the reason why we cannot apply PI controller here. What we do, we apply a PI controller, but we don't directly set the modulation index. What we do, we set the references of the current. And what we say is this. We say that this is the error in the output voltage, but we take a feed forward, we take the output feedback feed forward of the output current and add that to this current reference. The reason is simple. The current reference that we are setting is for this current, the inverter output current. Alright, and the inverter current and the UPS output current is the output current of this system. This is a disturbance, and if we do not take into account this disturbance, it becomes much tougher to control the system. It is easier if we take into account this inverter output, or rather UPS output, and feed it forward. Now what we are doing disturbance rejection. That's what we are doing here. We are doing disturbance rejection. Alright, and then after that we are going to do something. We are going to set these currents. Of course, these are all variable storage elements, but there are two which are very important. Inverter 1 control current ref T will be set to current ref T. Inverter 1 control current ref Q is set to current ref Q. What are these values? Go back here and check. You will see these are the same values. So we are applying a PI controller to the error of the output voltage, and we are setting the reference current. This reference current is now fed to the inner current controller. This is a double layered control. There is an outer voltage control, there is an inner current control. The inner current control we already saw in the previous lecture, and we already saw with the previous simulation. Now let's see how this looks like. Okay, so now this has been running for a while. Let's see if there's any result we can actually look at. So let's plot it again, the same thing. And here we see inverter output voltages .png, And you see, yes, they are indeed being regulated. You see, it's changing. It's interesting. Now the question is, this doesn't tell you much. It's not that easy. I mean, yeah, you can see it's 170 or so, but what really matters in control is to see. I can't understand why my computer is so slow. I mean, even Linux has become like Windows now. Yeah, good, it's closed. What we need to see, let's go back to the current control page. Yeah, always when you look at tracking, it is important to see what is being tracked. We are regulating the output voltage, the D component of the output voltage, to the reference D component. So if we want to see how the control is performing, we need to compare these two and these two. All right, so let's do that. Let's go find out if we've plotted them, and yes, we have. You see here, the reference voltage is this one and the actual voltage is this one. So let's go and plot it. And let's call this D tracking, or rather D voltage track, because later we might want to do current tracking also. So inverter control voltage dref, let's call this dref. Save waveform. Then after that we go to inverter voltage VD, and we call this VD. And let's click done. And let's check it out. Let's plot this first before going to Q. And you see here, the blue line is the reference, the orange line is the actual. So you see how misleading it is. If you look at this voltage, it gives you the impression as if it's actually tracking. It's increasing gradually, right? It's increasing gradually, and you see it's actually going close to 170. So you get the feeling it's tracking. But when you see this, you see it's not tracking. We are not there yet. I will, and as I'll show you later, it's getting there, but it's not there yet. All right. And now let's add the other one and see what's going on. Inverter voltage VQ ref, let's call this V ref, other VQ ref, save waveform, and always VQ, and that's it, we are done. And you see Q voltage tracking. So interesting graphs. Let's put them side by side. Let's put T here and let's put Q here. Alright, so a few observations. Now what I have done is, how did Q ref become 0 and VD ref becomes whatever the value is? It's actually minus 208 for that matter. Alright, because you might be thinking this doesn't make sense. Well, actually we are not setting the references, the values of VD ref and VQ ref. We are not setting these values. What we are doing is we are setting values of the actual ABC voltages, and I'm not sure if I've plotted them. No, I'm not plotting them. This is an exercise for you. You can add a variable storage element to the control file and add these and plot these values, right? That's an exercise I'll leave to you. We are actually only setting the reference values, ABC values, in stationary reference frame. But when you transform them, this is what you get. Alright. There's nothing wrong in these values. There's nothing wrong. This is not a wrong result. This is just what you get from DQ transformation. Because remember, DQ transformation is something which is based on how you are locking your frequency and how you're generating your phase angle. So it is not that, for example, the D will be high, D will be 208 and Q will be 0 or anything of that sort, or they will be half or anything like that. It only depends on the way you are setting your references, actual references of A, B and C, and how you're generating your phase angles. So as before, you see here, now next question, what exactly is happening? This doesn't seem to be tracking at all. Alright, you might think what's going on. I mean, this is at 0, all it has to do is stay at 0, but it's not that easy. The reason is, here this reference is at minus 208 volts and the Q voltage has to move to the negative value to be able to track this, and we'll plot it again. You'll see it starts tracking. But most importantly, you'll see here the reason is these two in almost all power electronic circuit with an inductance. When there is an inductance, the D and Q domains are linked with each other. Alright. So it is not possible to change D independently from Q or Q independently from D. And so when Q is changing, D also has to change. These two are coupled. Alright, these two are coupled. Any change in one does have an impact on the other. But with control, these two will eventually get regulated, and that's what we'll show. So let's plot it again. So this is my D, and this is my Q. So it has progressed a little, but still has a long way to go. Now that we have come here, let's also look at another control, that's current control. Let's see what the current control is doing. Alright, because that's also an interesting result. Is it the same as before? Let's check. So we see here current D ref. Now the question is, have I plotted it? And the answer is yes, I have plotted it. You see here, these are the actual D currents and Q currents, and these are the reference D currents and the reference Q currents. So let's plot these. Add a plot. Let's call this D current tracking. Inverter current ref T. Let's call this ID ref. You can name it anything you want. This is just names that I want. And then I shall call this current D, that is, I shall call this ID. And this is done. Let's add another plot. Q current tracking. And let's call this, no, it's not inverter current ref T, so let's call this IQ ref. and then there's inverter current Q, which is the actual current IQ. And we should click on done. And let's plot these one after the other. So let's go over and check the files. So first is D current tracking, and then there's Q current tracking. So let's go click on this. Oh, again I made a mistake. So as you see, it's the same mistake as before. These curves come in this order. So the orange swamps out the blue. So I should actually go back and reverse it. So let me go delete this plots and plot again. So anyway, these are little silly mistakes that you tend to make. So you can just delete this. And we shall delete this. Alright, so we first plot, again we go D current tracking, very good, it's there. It's just Google remembering what I did. And now we plot the value which is fluctuating, alright, because remember, this curve will come first, the next curve will be superimposed on it, alright. So plot the more, what do you call, more noisy curve first, and then we plot the smoother curve next, because the smoother curve will be superimposed on that. So we shall click done, and then we add another plot and we do the same thing again. Q current tracking, start plot, and again inverter we'll add inverter current Q, because this is the noisier waveform, and then we add inverter current ref Q, because this is the smoother waveform. So this comes first, this comes next. So we should be able to see both of them now. Click done. Oh no, I need to plot them. I just added them, I need to plot them. So we shall click on plot. And again on the other one, Q current tracking. So let's go over to the directory and you see a new one. And this is much better. So let's align them so that we can see them together. Actually, let's try to put all of them together. I'll just resize this and I will resize this. And then I will plot the voltage tracking and the current tracking. Let's put all of these together. And let's bring these two. Oh no. Well, it's a challenge to actually bring them together like this, but anyway. Okay, kind of okay. It's about as good as it gets. Keyword test tracking. Oh no, this is okay. I need Q current tracking. Okay, so this is as good as it gets. Oh no, it's just Linux deciding that I should maximize it. And it's frustrating, but anyway, let's zoom in a little here. Zoom. Okay, reasonably, at least you can see something. Let me just zoom this also. Unfortunately, there's no way to plot multi-plots yet. I'll have to work on it a little later. So, you see what's happening here. Q current and D current, they eventually start tracking. Alright? These two have started tracking, but initially there is a steady state error, and particularly with Q, there is a huge steady state error. Alright? The reason is because VQ ref is at minus 208 volts, and therefore IQ ref takes on a much larger value. And because IQ ref takes on a much larger value, but the actual current starts at 0, there is a huge steady state error initially. It takes time. You see here, it gradually comes, and here is when it starts tracking, current starts tracking. And that's why you will see this is the amount of time it takes for the voltage to come close to the reference. Alright, and the same here. This is when it starts actually catching up. Here there's a pretty big error, and after that it starts catching up. The reason is simple, because of this error here in tracking. This error here in tracking produces this delay, and this error in tracking, and because of this delay you have this coupled effect here. Even there is an error in the D voltage. So now that we progressed, at least we showed you these results. Let's plot it once more and see if it has progressed anymore. So D voltage tracking, and Q voltage tracking. So you see, let's look at this. Well, you see it's catching up. And Q voltage tracking. And you see, so as I said before, in almost every PI controller, you need to spend some time tuning your control value. So for example, you look at this, this is the reference, the actual value comes, it decreases, or rather because this value is negative, it decreases, it comes close to the reference, but then it overshoots. This is an overshoot. This is typically, the reason for this is simple: too much integrator or too little proportional gain. So there's two ways to go about it. One, you could try to increase your proportional gain and see whether this becomes a little better, or you could decrease your integrator and see whether this becomes better. Either way. So control tuning takes some time. So the important fact is this is working. So what I'm going to do at this point, there's no point running it again and again. I'm going to pause this video and I'm going to come back after a while when the simulation has run for a while. Alright. So as before, stay tuned, don't run away. I'll come back soon. Alright, so I am back. The simulation has been running for now close to half an hour. So I'm assuming some results should be available. So this is exactly where we left off. I'm going to close this and plot these two graphs again. Or waveforms, not graphs, waveforms. So let's go to D voltage tracking. Let's do a plot. and then plot Q voltage tracking. And let's go over and let's check. Oh no, I'm looking at the wrong one. See, remember D current tracking. So the name of the plot is exactly the same as the name of the, or rather the name of the file, except the spaces are removed. And you see, yeah, finally it is beginning to track. And there's Q voltage tracking. So again, actually this needed probably another half an hour or so, but I think this is good enough. This gives you an idea of what's happening. So you see here, this Q voltage overshoots rather, not exceeds, it overshoots this reference and then slowly comes back and starts tracking it. And as it starts tracking, you'll see that Q, the D component, also turns around, goes back to 0, has an overshoot and starts tracking. So if I let the simulation run, it runs for a second. If I let the simulation run all the way, you'll find that this tracking actually completely happens. That is, this voltage, the orange waveform, which is the actual voltage, will track the blue waveform, which is the reference voltage, with 0 steady state error. So in the meantime, let's go check what our other waveforms are looking like. So to begin with, let's check what the output voltage looks like. Because after all, this is the most important voltage. That's a control variable. This is the voltages that the output load will see. So let's go check it out. And as you can see, the output voltage also has a similar envelope as with respect to the actual D and Q voltages. The same way they have overshoots, the actual three-phase voltages also have an overshoot. The only problem is we zoomed it a little too low. So let's zoom in a little, let's say between 0.48 and 5. That's one cycle. So 0.48 and 0.5. And let's plot it. And let's look at output voltages again. And you see, well, there's a little bit of still flickers, and these are probably because it hasn't fully settled in. If you let the simulation run for a while, you'll see it becomes absolutely smooth and balanced sinusoidal. But most importantly, let's look at, if you look at this voltage reference here, you'll see that this voltage this peak will be close to 170. Alright, now it's tough to see here because we've zoomed in this way. You'll have to actually zoom in. Unfortunately, the zoom in feature is not really available, but at least on the y-axis, it's mainly the x-axis. Maybe I'll build that in next time. But this reference is actually now 170 volt peak. So now we have not only a three-phase sinusoidal voltage source, so rather sinusoidal set of voltages, but we also have them regulated with respect to magnitude. So this is a completely regulated, controlled voltage source. This is the advantage of the UPS. We have now done a two-layer control, that is an outer voltage control and an inner current control, to be able to achieve this. Alright, so I think this is it. I mean, for good measure, we can just plot the reference current and the D current reference and the Q current reference. I don't know why my computer is so slow. So there's D current tracking. And then there is Q current tracking. So let's go and check these two plots. perfectly tracking. Alright, there is no steady state error. There is a huge harmonic, there is a huge switching frequency harmonic, and that's only to be expected because this is a switching voltage. Alright, the inverter output is a switching voltage, and therefore there is going to be this ripple. But most importantly, there is zero steady state error. Now let's look at Q tracking, and also zero steady state error. So you see what has happened. This inner current control tracking has facilitated the outer voltage control tracking, because if this inner loop does not work, the outer loop also will not work. Right? The outer voltage loop is setting a reference for the inner loop, and if that inner loop cannot track its reference, the outer voltage loop will also not track its reference. Right? So now that we're here, let's plot the output voltage again. I'm not sure if it had progressed in much more, but let's look anyway. T voltage tracking. And then there is Q voltage tracking. So let's go over and let's look at D voltage tracking, and let's look at Q voltage tracking. I don't think it has progressed that much more. It will take quite a while for this to run, but most importantly, you see it is, and this is something that you can do on your own as an exercise. You can just let this run. All you have to do is let this run for like probably an hour or so, because I let it run for half an hour, and this is how far it got. So probably needs 1 hour. So as this goes on, this will become like a snake. It's going to wind around this reference, and the same goes here. And right, and when that happens, your output voltage is going to be perfectly tracking. So this is, with this I will end this lecture. I think that's all there is to it. Right? If you have any doubts or any questions or anything else, please do email me or message me. In the meantime, this is the last video of this lecture series, and the next lecture series will probably be on a microgrid formed with 2 UPS units. So there's going to be two of these UPSs with these control units, and then there's going to be a separate troop control algorithm that's going to achieve decentralized control of these UPS units. So that's going to come, but it's going to be a while, maybe a month or so before I get there. So in the meantime, I hope you enjoy using this simulator. Thank you so much for watching. Goodbye for now.